Okay, we're live. Good morning to you three again. And sorry about missing yesterday. We had lesson 4.5, which I think was pretty straightforward. The limits as x approaches infinity. And I want to see if you have any questions on that first.
17C, please.
17C, all right. So here's 17 in all its parts. On part C, okay, so here's the deal on C. What's the degree of the numerator? Pull that a little bigger.
Half.
Yeah, 1.5. And the degree of the denominator?
1.
Okay. Now, so we know that the numerator wins. So now what's the coefficient on top? Well, it's a negative 2x to the 3/2. So it's a negative. On the bottom, it's a positive, and that's why the answer is negative infinity.
Okay.
Could we also go through like 25, 27, 29, because they'll have like the same thing in common. But.
Yeah, so 25. Oh, you mean they all have roots or whatever?
Yeah.
Yeah. So here's 25, and we can look at 27 and 29 if you want to.
Okay, so you do have to rewrite it.
So on the top of this thing, we have x to the first. On the bottom, we really have x to the first. I mean, when you take x to the 2 to the 1/2 power, I know it's more complicated with the minus x here, but really that's all you have to do is look at the leading coefficient 2, and half of that is 1. So basically, the numerator and denominator tie. So you look at the coefficients, and they're both 1, so you'd think the answer is 1. But because the limit is as x approaches negative infinity, see, and on the bottom, what do we have? A positive square root. So we're going to have negative 1 over positive 1, and that's the reason it turns out to be negative 1. Does that make sense, Travis?
I'm still not sure I get the part with, because there's 2 x's there, what you're supposed to do.
So on the top, x is approaching negative infinity. Well, first of all, you see that the degree on the top is basically equal to the degree in the denominator.
That's the part that I'm not getting, I guess.
Okay. So you can ignore this minus x, because when x approaches any kind of infinity, that's just going to be so insignificant. Okay. And when you take you're taking the square root of x squared. So this is basically just an x. So in effect, we've got a first degree on the we've got a tie, a first degree on the top and a first degree on the bottom. The only issue you got to watch is x is approaching negative infinity, and this is a principal square root, so this has got to be a positive. And so you've got negative infinity over positive infinity, which really turns out to be negative 1.
Okay.
Well, got it?
Yeah.
Okay, let's take a look at 27. Same kind of thing. So on the top, again, we have a limit as x is approaching negative infinity. So on the top, so we've got a tie again. There's a first degree on the top and a first degree on the bottom. Of course, so because there's a tie, we got to go to the coefficients. So on the top, 2 times negative infinity is negative 2, and negative 2 that's a negative up there. And on the bottom, we have a positive 1, and negative 2 over a positive 1 neg, -2.
Okay.
Now, the book, I know I explained it differently than what you're seeing, because what they did is they divided everything through by x, and they come to the same conclusion. I just think it's a little easier when you. And 29, you had asked about that too. So this time, on top, we really have a first degree. On the bottom, we really have a first degree. So we have a tie. So the coefficients are 1 over 2. And here we don't have to worry about a negative because x is approaching positive infinity. So simply 1/2.
All right, that all makes sense.
Any other questions from the last time? Did I hear a 32? I can barely hear you. Would you say that one more time and speak loudly, please?
It's 33. She typed in
30. Oh, okay. Thank you, Maria. 33. Okay, so here's 33. Find the limit. So, what's the degree on the top? It's an equivalent of x to the 0, 1. X to the 0. What's the degree on the bottom? 1. And the denominator wins, therefore the limit's 0. So, by the way, just let me explain that sine x doesn't have much of an effect because, again, on the bottom, you've got 2 times this infinitely large number, so it's like 2 infinities, and the sine of x is puny. It's just a number between -1 and 1, so it has very little effect. So if you're wondering if the sine of x was throwing you off, maybe confusing you a bit. Okay, 31. Yeah, I could hear you a little bit better that time. Thank you. All right, 31. So I know the book, we've got a solution here, but here's how I would analyze it. Okay, what's the degree on the top? 1. What's the degree on the bottom? Well, it's 2 to the 1. You know, you got x squared raised to the 1/3. That's x to the 2/3. So on the top, you've got a limit of 1. On the bottom, you have a limit 2/3. Which one is bigger? The top. So as x approaches infinity, this is going to go to infinity. So my style, I prefer this answer right here. Yes, when you say something has a limit of infinity, in effect, you're saying, so in other words, there's no limit because infinity isn't a point. It just keeps, yeah. So, yeah, I just rather just say infinity. Did that make sense, Maria? Wow, can barely hear you. Okay. All right. Does anyone else have a question on lesson 4.5? So here's the new lesson. And really, it's not a new lesson. It's a bunch of things that we've learned kind of gathered together to help us sketch graphs. So the good news is really nothing new today. We're going to be gathering a lot of tools that we've already learned together to help us with a graph. So these are kind of, yeah, I mean, and you'll see we've got quite a collection. But first, I just wanted to share a little bit of humor with you. I just came upon this the other day. This was on Kentucky television. Thought this was pretty hilarious. Talk about the dangers of spelling wrong. 5 arrested in math lab bust. Is math illegal in Kentucky? Obviously, that was supposed to be a meth lab. Anyway, I just thought I'd share that with you. The person who made the spelling mistake did not want to be identified because it was too embarrassing. So anyway, just so you know, math is not illegal in Kentucky. Okay, so back to curve sketching. So we're going to apply a bunch of old things. And here are some of the tools we've gone through, and you can see what section they were in. I mean, x-intercepts, y-intercepts, wow, that goes way back to section 1.1. Symmetry, again, likewise, the very first lesson of the year. Domain and range, first chapter. Continuity, you know, does the graph have a break in it? How do you tell if it does or doesn't? Vertical asymptotes, differentiability, and we learned that there were, a couple of cases where you can't differentiate. Relative extrema, that we did at the beginning of chapter 4. Concavity, we just finished that, lesson 4.4. Points of inflection, changes from one concave to the other. That was in lesson 4.4. We really just talked about horizontal asymptotes in the section we just, and limits at infinity. You put those all together, and you really got some interesting information. You can almost, even if you have no idea how to graph something, you put all those clues together, and you can do a pretty good job. So let's dive in. Here's our first example. We have a rational function. Make that a little bigger for you. We have a rational function, 2 times the quantity x squared minus 9 divided by x squared minus 4. So all these crazy things we've learned how to do. So, you know, we should look at both derivatives. So you notice right away they start off the list with the first derivative. And of course, to do the first derivative, we'd have to do the quotient rule. Now, I don't know if you want, let's just talk about the first derivative. Okay, so if you did the first derivative the long way, what would you do? You'd have to do the quotient rule, right? Denominator times derivative of numerator. And here we have a product rule, right? First times derivative of second. Plus second times derivative of first, which is 0. Okay, so denominator times derivative of numerator minus numerator times derivative of denominator all over denominator squared. And if you simplify that numerator, you know, you're going to wind up, you know, so let's just show you what happens on top. So this is really a 4x here. And 4x times x squared minus 4 is, I'm sorry, 4x times x squared minus 4 is 4x cubed minus 16x. And then over here, 4x times that is again minus 4x squared. And negative 36x. And when you simplify that top, what do you get? Oh, this is supposed to be 4x cubed. You get the 4x cubes wipe each other out. And this is actually a plus, and so you wind up with 20x on top. So anyway, they simplified all of that. But anyway, And then you could take the second derivative. Okay, so why do we want to know the first and the second derivative? Because we know that when the first derivative is equal to 0, we're going, or when the first derivative is, what do we call it, undefined, then we have a critical point. Notice, when will the first derivative be 0? You can see on top when x is 0, right? The only time a fraction is equal to 0 is when the numerator is, and that's going to be when x is 0. So 0 is a critical number. And on the bottom, we've got a problem when x is what, 2 or negative 2? Because when x is 2 or negative 2, that's going to create an undefined derivative. So you see how that's pointed out here. And here's the critical number. Okay. All right. Anyway, you start putting all the pieces together. Asymptotes. How do you find asymptotes? Well, when y equals 0, and again, when will this whole thing equal 0? When the numerator is 0. When will the numerator be 0? When x is 3 or negative 3. So now we know, hey, that's where it crosses the x-axis. How do we know where it crosses the y-axis? Well, that's when x is 0. So you're going to get what? On top, 0. You're going to get 0 minus 9, which is negative 9. 2 times negative 9 is negative 18. And on the bottom, negative 4. And that equals plus 9 halves. And that's where they got, the y-intercept. Horizontal asymptote at 2. Why? Because as x approaches infinity, what's the limit of this as x approaches infinity? Look at the original function. As x approaches infinity, notice x, the tie between the degree on the top is 2, on the bottom is 2. So we go to the coefficients. Oh, 2. So all that stuff we've been working on, you wind up with all these things. Okay. And then you can put this all together. Now they make up a chart to really, really in a detailed way, kind of put this stuff all together. And, you wind up with a graph because, there's our intercepts, negative 3 and plus 3. There's our y-intercept, 0, 9 halves, 4 1/2. We knew we had asymptotes at 2 and negative 2. There they are, vertical asymptotes at 2 and negative 2. We know that as x approaches infinity, it's going to go to 2. And because I don't have the graph up, I can't show you. But as this goes out to the right, it's going to approach 2, and over here 2. And, oh yeah, and what about concavity? Well, concavity is what? You can see from negative infinity up to negative 2, it's decreasing and concave down. That's this part. Again, we all got that from our concavity tests. And from 2 to infinity, it's increasing, concave down. And between 0 and 2, it's concave up. And that's this part. So anyway, the whole idea is when you get strange functions, we didn't use symmetry, did we? They didn't use, oh yeah, they did. Why does it have symmetry with respect, here we are right down here. Why do we have, where did they get that from? Remember how to do symmetry? It's been a long time. Symmetry says if you plug in a number for x, like for example 2, get your answer, and then plug in negative 2, and then do that with a few more points, 3 and negative 3, maybe 1 and negative 1, and if you keep getting the same answers, that tells you have y-axis symmetry, and that's what we've got. Sure enough, look at how this has a nice fold line on the y-axis. You put that stuff all together, and you really wind up with a snapshot. And of course, you can check this, but even without any kind of Desmos calculator, whatever, we can pretty much come up with what this thing looks like. So the idea is to use all these old, I shouldn't call them old, but all these tools that we have learned how to use this year, put them together, and put all these hints together to come up with pretty much what the graph looks like. Okay, let's look at a second example. So this one was a rational function. Example 2 is another rational. We got a little bit more of a complicated numerator though. Now you're going to notice that when the book does its first and second derivative, when they do their first and second derivative, do you see how they often have them factored? So in other words, instead of writing on top x squared minus 4x, they wrote it as factored. And likewise on the bottom, well, that's pretty obvious because what? When you do the quotient rule, you're going to wind up with the denominator squared. So that's not a surprise. Why do they show that numerator as factored?
Doesn't really make sense to. Wouldn't it be harder to take the derivative doing that?
Wouldn't be harder if what?
So wouldn't it be easier to take the derivative if you left it unfactored?
Well, except, see, when you do this, here's what this looks like. Here, let's just do it the long way, okay? So the derivative is what? The denominator times the derivative of the numerator minus the numerator. I'm going to need to move this over a little bit. Minus the numerator times the derivative of the denominator. Well, that's 1 all over denominator squared. Okay, you can see the denominator coming out. So on top, x times 2x is 2x squared. X times negative 2 is negative 2x. Negative 2 times 2x is negative 4x. Negative 2 times negative 2 is plus 4. Then we have to subtract that thing. And what happens on the top? Well, on the top, you get 2x squared minus 1x squared, which is x squared. Negative 2x minus 4x is negative 6x. And when you subtract a negative 2, it becomes negative 4x. And 4 minus 4. So, in other words, here's what you get. So, that's really what we've got right here, isn't it? But why did they write it like this?
Maybe easier to see the zeros.
Yeah, because what's important is to, thank you, you're both right. You want to find where the first derivative is 0, right? Because when the first derivative is 0, we know we're going to have critical points. So it just makes it easier to do your next step. So you'll see the book will often write it this way, which is nice. So you can just look at it and say, hey, when will this be 0? Well, when x is 4. Okay. But when will this derivative also be what? Undefined. When x is 2. And you see how you can see them. So right away, if you look down here, oh, and on top, when else will this be 0? When x is 0. So we found out basically both of these things, that when x is 2, you got a vertical asymptote. when x is 0 and 4, those are critical numbers. Okay, so anyway, and then when they did the second derivative, again, there's a bunch of simplification that has to take place, but you wind up with this. You can see, when will the second derivative be 0? It won't, because the numerator, 8, will never be 0, and hence, possible points of inflection, none. All that stuff becomes visible when you put those in factored form. End behavior, that just means what happens when x approaches infinity and when x approaches negative. So if you just look up to the original function up here, what's the limit of this as x approaches infinity? Well, the top has a power of 2, the bottom has a power of 1, the top wins, and so that limits infinity. So as we go to the right, this thing's going to get forever higher. And this says, if you make it negative infinity, so sure enough, if you look at the graph, which I guess is cheating, but we're going to peek ahead, on the left side of the graph, you can see it's forever going to be going down when we go to the left over here. And when we go to the right, this thing's forever going to be climbing to positive. And so you can see that that matches up. Where were we going to have, do you remember, where were we having asymptotes? Oh yeah, x equals 2. Sure enough, x equals 2. Whoops, sorry. X equals 2. We have a vertical asymptote. All that stuff starts coming true. What about concavity? Well, we don't have any, what do you call them? We don't have any points of inflection. We figured that out right here. So what kind of concavity do we have? Well, look at the second derivative. So when x is less than negative 2, what's going to happen? I'm sorry, when x is less than 2, what's going to happen? This is going to be a negative down here. And what happens when you cube a negative? It's going to be negative. And 8 cubed is a positive. So positive divided by a negative, negative. So when x is less than 2, we're going to have concave down. Sure enough, when we're to the left of 2, you see how we have concave down here on the bottom. And when x is to the right of 2, we're going to have a positive cubed on the bottom. Positive cubed is a positive. Oh, that's going to be all concave up. And sure enough, when you look at the right side of this thing, it's all concave up. So all of that comes together, and we have learned all kinds of really cool stuff about this graph that otherwise would be a little bit mysterious. And our third example, this time we just have a good old polynomial. X to the fourth minus 12x cubed plus 48x squared minus 64x. So right off the bat, let's factor it. You notice how there's an x in every term? Yep, you can take an x out of that, and when you take an x out of that, what do you have left? Turns out that's actually a cube. So look, here's the, here is the factored version of the original function. Why would I want to know when the original function is factored? Because that tells when, so you look at this and say, hey, when does this thing cross the x-axis? Oh, when it's 0. Are there, notice there are 2 places when this crosses the x-axis, 0 and 4. So we just found the x-intercepts right here. Okay, that's cool. Those are anchor points. You can put those on your graph. You know those are there. And then the derivatives are more straightforward this time, but again, you see how they have them in factored form? So can you tell where are the critical points? Sure, just look at the first derivative. Because it's in factored form, I can see that happens when x is 1 and when x is 4. So there's our critical numbers. When is the second derivative equal to 0? when x is 4, and when x is 2. So those are points of inflection. Do we have any asymptotes this time? No. Why not? No vertical asymptotes because we're not even dividing by anything, are we? Nope. Horizontal asymptotes, in other words, what's the limit of this as x approaches infinity? It's going to go forever high, right? Because it's just x to the 4th is the ruling term. And when you plug in infinity, that's going to be infinity to the 4th. It's huge. Likewise, if you plug in a negative infinity, it's still going to be what? Positive infinity, right? Because when you take a negative number and take it to an even power, it's going to be positive. So this thing is forever high on the left, forever high on the right. So you put it together, it's a little bit hard to show this, but the green is the graph, and it's coming from positive infinity down, and it goes down to a low point down there, and then it comes up and does this little curlicue, and then it goes on up forever to the right. So where is our low? Well, we predicted that, didn't we? We said there's critical numbers at 1 and 4. Well, at 4, you can see there's like a what? A point of inflection here, right there. And at 1, sure enough, it's our low. I don't have decimals up here, but we could, that's 1 comma something. Let's put that one in decimals. Just get her straight here. I got to write her down. X to the 4th minus 12x cubed plus 48x squared minus 64x. X to the 4th minus 12x cubed plus 48x squared minus 64x. So this is that graph I was showing you. There's our low point right down there. 1, negative 27. So there's our low. And then if you look up here at 4, 4, 0, you can see it changes from concave down to concave up. So yeah, that all makes sense. So, I mean, I'm not requiring, so here's the idea. With the problems that I've given you, or that we're going to look at on the assignment, use as many tools as you can. You don't have to use them all. And then try to sketch a graph and look at as many details as you can. These problems take quite a while to do. And then when you're all done, go ahead and check it on decimals. And that's kind of the idea behind today's work. Let's see what we've got here. So this is 4, 6. So you notice I've only got 4 problems for you here. Number 5, number 11, number 19, number 65. That's enough because each one takes quite a bit of time to go through and look at all these different aspects. So, questions? Do you want me to go back over any of the examples?
Should be all right.
So this is kind of a gather a bunch of tools that we've already learned how to use, although you might need a little review to review them. And from all of those, get all these clues about the graph, and then try to make the graph, and then should be able to, and then check it using technology. And that's basically the idea today. So my two ladies, did you have any questions?
No.
Well, thank you. Have a good day. I hope we get past this drippiness a little bit later. And I will see you tomorrow.
All right, see you.
Thank you.
You're welcome. Bye.
Bye.